Chapter 23, Medium Difficulty Buffer, similar to a weak base plus a strong acid titration. Calculate the pH when 50 milliliters of 0.40 molarity ammonia is mixed with 50 milliliters of 0.20 molarity hydrochloric acid. So first off, let's touch on this 1/2 VE. This is usually written like this, 1/2 VE. And it means 1/2 equivalence volume. In other words, our volumes here of our weak base and our strong acid are equal to each other. So that's important. That'll come up later when we use the equation that's associated with buffers. What is the equation that's associated with buffers? It's the Henderson-Hasselbalch equation. We know that'll come up later when we're solving for the pH. So, step 1, identify the major species. So, we have ammonia, which is a weak base. You should have that memorized by now. And we have hydrochloric acid. Oops, don't know why I switched colors, but I'm going with it. This is a strong acid. Okay. So now, as usual, we'll write out the reaction. So for this one, since we're mixing together an acid and a base, I'm going to go ahead and include them in the same reaction together. If you have an acid with a base, sometimes writing them together, it's easier to create that net ionic. So NH3 plus HCl. All right, well, I know I'm going to go ahead and make this reversible because I know that the NH3, no, actually I'm not. I'm going to leave it like that. So the NH3 plus the HCl, I know that my NH3 is going to form NH4 plus. It's going to grab that hydrogen from the hydrochloric acid, which is going to leave behind this chlorine ion. Now I want the net ionic, so let's split this up even further. I know my weak base stays as a whole. However, my strong acid, because it is strong, gets split apart. Here is my ammonium and my chloride ion. And I can see that my chlorides will cancel each other out. So my net ionic, which is what I will use from now on, is ammonia plus hydrogen reacts to form ammonium. All right, now let's, well, can I do the ice chart yet? The answer to that is no, I can't do the ice chart yet because these two things have been diluted. So I need to do a dilution first. So dilution. I'll do this for both of them. NH3 will come first. So it starts off at 0.40 molarity and a volume of 50 milliliters. And we want to know what its new concentration is after it has been diluted or mixed with another 50 milliliters. So I'll have an M2 of 0.20 molarity ammonia at the very beginning, whereas my hydrochloric acid started at 0.20 molarity and also 50 milliliters. And it also got diluted to 100 milliliters. So our M2 here is going to be 0.10 molarity. HCl, which I know splits apart immediately into hydrogen and chloride ions. Okay, Step 4. Now that I have these concentrations, I can set up an ice chart. ICE. I'll use my net ionic here, so NH3 plus those hydrogens from the hydrochloric acid will react to form NH4. Okay, so I know I started with 0.20 molarity ammonia as well as 0.10 molarity hydrogen, and I don't have any ammonium. I haven't treated this with a salt to make the buffer stronger, so there's that. Now I know that this strong acid is going to release those hydrogens, and those hydrogens are going to want to react with whatever they can, so I'm going to go ahead and say that they all got used up, whereas these guys were limited by the amount of hydrogens we had. There. So we ended up at the equilibrium with 0.10, 0, and another 0.10. Hey, would you look at that? We have equal molarities of our weak base and its what could be considered its salt, or its ion, its conjugate acid. That is going to come up now when we go to solve for the pH. So when I solve for the pH, I need to use the Henderson Hasselbalch equation because it's a buffer. So we know that equation could be written in terms of pH or pOH. In this situation, we are dealing with a base, so I'm going to write a pOH. This will be equal to the negative pKb plus the log of the base on the bottom, which is ammonia, and that base is ion on the top, which is ammonium. Okay, so the pOH, what does P stand for here? It stands for log. Our Kb was given to us, or it would be given to us as this, 1.75 times 10 to the negative 5, plus the log of these concentrations at equilibrium, which we have, and oh, they are exactly the same. Now, if you were to plug in the log of 0.1 over 0.1, you would just end up with 0. It comes out to 0. So in this situation, the pOH is going to be equal to the pKb, or the pKb. So that's pretty cool. Let's actually figure out what it is, though. So what is the negative log of 1.75 times 10 to the negative 5? I should say it's equal to the negative pKb. So you end up with 4.76. We have 3 sig figs in here, so I guess I should say actually 4.757. Okay, so I know the pOH, but this problem asked me to solve for pH, and I know that pH at 25 degrees C, which is what we're assuming all of these problems are at, will give us 14 minus 4.757. All right, so you end up with a pH of 9.243. So even though we added a strong acid to the situation, our ammonia, our weak base, acted as a buffer, and it prevented that pH from dropping too much, which is good. It did its job. So if you're going to write an annotation on here, something that's, important for you to remember is at the 1/2 volume of equivalence, the POH is equal to the pKb, or you could say that the pH is equal to its pKa. Because if you plug in equal volumes in this piece right over here, you just end up with 0. That whole little chunk just goes away. And that's how you solve this type of buffer.